So as far as administrative stuff goes today, we have a date for the midterm too now. It'll be on November 9th, which is 2 weeks from today. And then we'll do review the class before that. So next Thursday, we'll do some review for that. It's going to cover everything that we've done so far. So pretty much everything up to today, which if you look at the syllabus is everything aside from stacks and queues, which is what we should hopefully talk about today and maybe tomorrow, depending on how long it takes. And that's the last topic that's on the syllabus. So that'll be the only new topic that's on the final exam, and it's relatively short. There's not a whole lot to cover with it. We'll probably get it done by today, I assume. On that note, I did put up an announcement on Canvas about topics to talk about afterwards, since we are going to have some extra time. Probably next class, and then the class after that before the review, and then everything between the midterm and the final. We are going to have covered everything in this class, so I wanted to see what everybody wanted to talk about. I put up a list of topics, but if there's anything in particular that you're interested in with regards to computer science or just general programming, feel free to leave a comment on that announcement, and we can definitely talk about it. If not, I'll just probably talk about things that apply to other CS classes, and then maybe development if we have time. And then assignment 6 got extended to tonight. We're going to talk a little bit about one of the functions here, just what it means, since I did get quite a few questions over the weekend on that. And then I want to talk a little bit about assignment 7 stuff as well. Assignment 8 should be up hopefully within the next day or two, so you can just get started on that early if you want. So I think that's everything administrative. Let's go ahead and talk about that then, the linearized array. So this is specifically for the create matrix function that exists. Most of the other functions you'll see are very similar to the code that I wrote for that one example with the matrices a few weeks ago. I guess I didn't know what assignment 6 was going to be in advance, so I just happened to do matrices for operator overloading because I thought it was a good example, because you can overload pretty much every operator for it, and it just turned out to be the homework. So that's probably a good thing. But there is one thing that was not specific to matrices, but it was just like part of the assignment that I got a lot of questions on, and that's linearized arrays. So generally, you want to store a matrix or some 2D array in rows and columns. So let's say I have a matrix or array, either way, that looks like this, and it's 2 by 3, 2 by 3. And so we have these rows and these columns. Now, the way we normally index these is there's a row number, and then there's a column number. And then if this was just called, let's say, matrix, then you would access it this way, where you'd say matrix some number between 0 and 1, inclusive, and some number between 0 and 2. I'm just going to use I and j to represent those, just being some integers in this range of row numbers and column numbers. Now, we've talked a bit about memory and dynamic memory allocation, and we've mentioned a few times that when we do memory, it's always in a straight single file line. It's always one-dimensional, because RAM is one-dimensional. It's just a set of addresses that represent where the bytes go, right? We always had something like this in our drawings, and we would say this is, hex 0, hex 1, hex 2. So it's just counting numbers. Therefore, it's kind of like a number line. It's one-dimensional. And because of that, any sort of allocation we do is always going to be one-dimensional. If you're doing a dynamic allocation of a 2D array, like we've done in the past 3 assignments that you're hopefully used to by now, then we allocated like a column, and then we allocated rows after that. So even though it's 2-dimensional in the way we access it and kind of the way we view it as an abstraction, it's really a 1-dimensional column and then 1-dimensional rows, right? Is the way that we've done 2D arrays dynamically. And even though you can declare an array statically, like you would have done in CS135, then even if we view it this way, again, it's kind of an abstraction. It's stored a little differently than this, but it is still in a straight line. No matter what kind of array you make or any kind of data structure that you make, it always has to be allocated somewhere in that straight line of memory. And so the way that this part here works, I'm going to erase this other diagram just so we have some room. Can I make this bigger? Okay, good. So the way it actually allocates this is not two-dimensional because RAM is one-dimensional, so we can't really do that. Instead, it just puts it all in a straight line, and then when we do these array accesses, it actually just calculates where that needs to go. So let's discuss how we do the calculation, and then how we can reverse that as well, which is what the assignment was. So let's just say that I fill these in order 1, 2, 3, 4, 5, 6. The way it's generally agreed upon is row first, then column, like you're reading a book. So you start at the top left of the page, and then you read the line, and then you go down to the next line, and you read that line left to right, right? So that's just the generally agreed upon way to store these. You can certainly do a column first, but that's just what's considered commonplace. And so what actually happens in memory is that it goes and allocates these 6 things all one right after the other. 3, 4, 5, 6. And so these things are all row 0, and then these ones are all row 1. And then we can see in terms of their column numbers, this would be 0, 1, and 2, and that's numbered within the row, which is just a segment of 3 in this case, and then these would be 0, 1, and 2 as well. And so that's how it's actually stored. And this is what the indexing does essentially, is whenever you access an I, it says, I'm going to skip forward by that many I's. So if you said, for instance, that you wanted to access matrix position 0, 1, what it does first is it goes to the I, it says, I'm going to go to the 0th block, which is 0 groups of 3, so it jumps forward 0 spaces from the start of the array, which is here, and then it jumps 1 space after that, which is, right here where the 2 is, right? And if I was to instead go to, let's just say, 1, 0, then what it does first to go through the rows is it jumps to the first block, which is 1 times 1 being the amount of rows that we have, and 3 being the number of things in that row, many spaces forward, and then it jumps 0 forward, so plus 0, and then it ends up at 4, which if we look here is what's at position 1, 0, right? An actual thing. So if we wanted to come up with a generic formula for this, then the idea is that we have some knowledge of how many things are in the rows. So let's just say that this is number of rows by columns, which I'll just call calls. Then we know that if we're indexing it this way, we'll just say this is I and j, then it would be I times the number of things that are in a in a row, which is the number of columns that there are, plus j. Right? And if we kind of think that out, that makes sense because these are just groups of columns. If we think about it, rows are just groups of column elements. And so if this column is 3 in this case, and we wanted to get to the element 4, which is at position 1, 0, then we would go 1 group of 3 forward and then an extra 0 after that because it's just in the 0th position. If we wanted to access 5, it would be 1 group of 3 and then 1 extra space to get to 5, if that makes sense. So we do I times whatever the groups are plus the offset into that group, which is j. And if you did multi-dimensional arrays that are like 3 or 4, you'll notice it follows a very similar pattern where you just multiply by how big a certain dimension is, and generally it's going to get bigger into like squares and powers of 3 and 4 if you go into higher dimensions. Generally though, whatever this number is going to be 1 degree less than the dimension of your array. In other words, the amount of terms that are in your polynomial that generates the actual correct index is going to be equal to the degree. So we have like 2 terms here in a 2D array. If I had a 3D array, I would need to have k, and there'd be a k term where it has columns and rows included, or columns and whatever we would designate as the third dimension. We won't worry too much about that. That's beyond the scope of this class, and honestly not particularly common to encounter. But this is just our general approach right here. Is we want to skip over some amount of columns in each row and then go into that row and find it. Now, what the assignment is asking for is to do this kind of backwards. So this process is known as linearization. That is, you treat a 2-dimensional array as if it's a straight line, like this. Pretend it's that way. What we're going to do is kind of like the opposite of that. And generally, this is a good idea, actually, to store your arrays. I know we've been doing 2D array allocation with the column array and then the rows array, but if you know how to do this math, it's actually a better idea to store everything contiguously and then just access it using that indexing. You do have to incur the extra steps of like doing the math to find it, but you are guaranteed that the memory is like all together at any given point, which can be a little helpful from like a hardware point of view, because generally things that are close together run a little bit faster. But anyways, let's go ahead and try to do this backwards. So let's go from a 1-dimensional array to a 2-dimensional array. Let's go ahead and put new here. So let's say, again, I have this 1D array with those indices 1, 2, 3, 4, 5, 6, and I want to go and access it as if it was a 2D array. And then these are the actual indices. And this is what the create matrix function is asking you to do, is you want to take in a index into this linear array and convert it into an access into the 2D array. So in that assignment, there's a 10 by 10 matrix, and you're going to take one single number between 0 and 99, because there's 100 things in a 10 by 10 matrix, and then find out which element is at that position. And so the way we can do this is we need to do it kind of backwards from how we did the other one, where we grouped it up and then added an offset. Is we need to figure out what the offset is going to be, and then we need to figure out how many times we multiply by that number. Right, so essentially with this backwards part here, what we need to do is go from our answer So whereas if we go from a 2D to a 1D, we're given this and this, and we can solve for the index. What we need to do here is we need to go from the index to the I and the J, which if you notice is a little bit harder algebraically, because like these are both unknown. But if we know the columns, we can actually find it. So again, we know in advance that the 2-dimensional thing is going to be a 2 by 3, and so we can use that to figure this out. Let's say I was to go and access any one of these things, the 1, 2, and 3, then they're at index 0, 1, and 2. One thing to notice about that is that they're all in the first row together, and then as far as these 3, 4, and 5, these would also be at position 0, 1, and 2, but they would be in row 1 instead. So we know that it's going to keep going in this pattern where the row that these should be in, or sorry, the column that these should be in should be 0, 1, 2, 0, 1, 2, 0, 1, 2. If this was to keep going on forever, right, 6, 7, and 8 would be in column 0, 1, and 2 if I was to extend this out further, right? And then the only thing that goes up every single time is the row number. So these are all in row 0, these are all in row 1. So I guess, does anybody remember any sort of operator that we can use that that is able to do this repeating part? So like every time you hit a number, it restarts counting. Right? So I see in the chat, modulo, you're right. So modulo is a wraparound operator. It always takes the remainder of something. And so whenever you hit something that's divisible by that number, it restarts counting at 0. In this case, we know we have 3 columns. And so whenever we hit a number that's divisible by 3, 0 and 3 being those two numbers, we reset back to 0. So then this blue part right here, that is the modulo. We can modulo our index, and it will always give us what we're looking for. And then what do you think the row would be then? So what's the other part that goes along with modulo that tells you, in other words, how many times that number of columns goes into the index? Right, so you said division? Yep. So division tells you how many groups of things you've had. So these numbers would be, sorry, I guess we should look at the green ones. These numbers would be numbers that 3 goes into 0 many times. These numbers are ones that 3 goes into 1 time, and then these are the remainders. So what you can think about for division and modulo, just in math in general, is that division tells you how many groups of things you have, which is what it represents, right? It's the opposite of multiplication, which is a grouping operator. And then modulo is something that tells you the offset into that group if you're counting in a specific order. So if we want to go the opposite on here, where this is the index into the linearized array, then all we have to do is take the index divided by the number of things in a row, which is the column count. And then after that, we take the modulo by the number of things in the column. Or sorry, in a row, which is the columns. This being our j, and this being our I. And this is the formula that's given in the rubric. Just to clarify, what that function is saying is that it wants you to take this index and convert it into a two-dimensional version, which is how the array is actually being stored. So by using this formula, you'll be able to access that. So you want to go in that function, go through all of the elements in the array you're copying over to, which I think is this matrix. I think it's a non-static function, so it's just whatever is calling it, and then access the past A array by copying it over in this way. So you just need to use this formula. Now, in that case, the column number is a constant. It's always a 10 by 10 matrix, so you can just put this as 10 if you really want to. Or I think there is a column constant as well. So that would be the way to do it. I think the rubric says divide by 10 mod by 10, which is fair, but I would kind of prefer that you don't use magic numbers. So this is just the generic way to do it, if that makes sense. Does anybody have any questions on why this works or the math or anything? Okay, fair enough. Don't see any questions. So hopefully that helps a little bit on assignment 6, which again is due tonight. That's fair. So the implementation part, I'll just give you a hint. It's not as hard as it seems. Really, you just got to use this. Just do 2 for loops that access the array that you're writing to, and then just read a single number and do this. It shouldn't be more than about 4 lines of code. So don't overthink it, I guess, is all I'd say. Right, so before we get into the part about assignment 7 or the data structure associated with it, I wanted to just briefly mention 2 more things about linked lists. They just kind of crossed my mind. We've technically talked about it, but I just want to explicitly mention it. Let's just say we have another linked list, if you remember from last week. That's just a structure where we have these nodes that contain some data and then a pointer to the next node in the list. And then we keep track of the head, which is just the starting point of the list. And we talked about deletion, where we needed to keep a previous node and then a current node. And then we delete the thing and kind of make the pointer go around. What I wanted to talk about was a de-allocation. So what you would ideally write if you were to write a destructor for a linked list, which I should probably add to the linked list code on Canvas because it's going to have a memory leak with what I uploaded. So let's just talk about that really quick. If we think about what a de-allocation is, it's just like removing all of these things, right? Which is the same as deletion, which is an operation we talked about, but it's just a deletion of everything. And because of that, we're not expecting to need to use the list again after its de-allocation, which means we don't need to update the pointers at least. That's something convenient about this. But the strategy for doing this is much the same way. So consider if I keep a head and then just deallocate the thing at it, like this, where I just say delete head, then that's a little difficult because then now I've lost a pointer to the rest of this linked list. And if I was to try to like store something, equals, we'll just say head next, delete head, do the same thing. Then we have some pointer here, we deallocate this thing, and now if we want to deallocate the next one, we're going to need to do the same thing because we're kind of stuck at the same point. If I just delete the current again, I have an issue. So we need some way to traverse this. So let's just address 2 ways. One way would be to do what we've had previously, where we just keep a previous and a current. And I think this is the easy way to do it explicitly, at least. So what we do is we would set a current equal to the first node, a previous equal to the head, and then we could just loop while we still have things left that we need to deallocate. So we just say something like while current doesn't equal null. In fact, I would probably say while previous does not equal null. Actually, I guess that's probably what we want. Current does not equal null, pointer. Then go ahead and delete things and then update, which would just be deleting whatever the previous node was and then updating them the same way that we've been doing before. So we just say current equals current next. Remember, this just moves the pointer to the node to the right of it. And before I do that, I should set previous equal to current. And we can't do it with the method of previous equals previous next in this one because previous is now deleted. So that would be a segfault. Just be careful there. I'm having some trouble writing around that. Well, looks good enough, I guess. Right, so this should be okay. I think it does leave the last node, so you'd probably need to go down here and delete previous one more time after the loop. If we kind of consider the break condition, this would have the current be here, it would delete that. It would have the current be pointing to this, it would delete this, and then it would make the current equal to null before it actually deletes it. So I think that's what happens. So this is just generally the code for that. It just felt like I should mention that you should add this to your linked list class, and I just forgot to code it. But it's not that much different from our deletion. There's another way to do this that I kind of prefer to do, which is, so I'm just going to write it over here. Let's say we have the same linked list. This is an example of where I think recursion makes something a lot easier. So the way I generally implement this, if I have to, which is not very often because I don't think I ever write linked lists, is I actually just write it like this, where I say delete head, and that's it. And the way we can actually get this is by having the node deconstructor recursively delete the next thing. So consider that what deletion does is it just calls the deconstructor. Oh, I have a question. Is there any benefit of using null pointer over null? I think they're the same constant. I was told null pointer is safer, but I'm not entirely sure why. I guess null just might be deprecated or something. I'm not 100% sure. But as far as I know, they're both constants and it should be okay to use both of them. I kind of prefer to write null, if I'm being honest, just because that's what C# does and that's what I'm used to, but it should be okay if you use either. But yeah, just consider what a deletion does is it calls the deconstructor of an object explicitly. So this is technically a function call. And because of that, you can then recursively call a deconstructor. So what I'd simply say is if next does not equal null, basically just do an error check. This should be null pointer, yes. Null pointer, then deletes next. And if we consider what this does, is it goes and calls deletion on the head, which is this one. And in the heads destructor, so this goes ahead and calls the heads destructor and it says, okay, if the next is not equal to null, which it's not, then go ahead and delete the next. So it goes and tries to call this next one and it says, okay, delete this guy. And then this guy calls its deconstructor and says, okay, I'm going to delete myself, and my deletion is to then delete the next guy, which is this one. And he gets there and says, if next does not equal null pointer, delete next. Well, next is null pointer because it's the end of the list. And so this guy gets deleted when his deconstructor finishes. Then this one doesn't have any other code because its only job was to call this one's deconstructor and deletes itself. And then we get back to here where it just asks to delete the head. So we can recursively write a way to do a linked list deletion. And I honestly think this is way easier to do because it's like, what, 3 lines of code? Although it is recursive, so it is a bit slower. But generally, I think this one's kind of nice. If you have more complex nodes, though, I think this can sometimes cause issues. But if you're just doing a singly linked list, I don't know, this one works pretty well for me. And again, just to go back to harping on about recursion, this means that base cases, don't have to be something super hard to find like a constant, and that our reduction operator doesn't have to be subtraction or anything super conventional. In this case, the reduction operation is deleting the next node. So the delete keyword can also be used to do recursion. And reduction operations don't have to be super straightforward. Okay, so that's just one extra note about linked lists. Let's talk a bit about circular arrays, or as the assignment calls them, ring buffers. And we'll tie this back to linked list, I guess, in a second. So for assignment summit, you're going to have to implement one of these, and they're occasionally useful, so I think it's a good thing to know these ring buffers exist. And what they are is just usually a static array like this that you have allocated of some amount of size. You can do these with a linked list as well, which we'll show in a second. But generally, I would just say do it as a static array. And what it does is it's used for things where you only need as much as what's going to go into the array and nothing more ever. Potentially less, but never any more than what's in the array. And you're expecting to get a constant.
This meeting is being recorded.
Oh, did I not hit record before? I don't know if anybody else heard that, just the recording noise. Okay, well, hopefully it was recording it. Anyways, yeah, assuming you're getting some sort of constant stream of input and you don't want to use like extra space. I think the rubric mentions that you can use this for like input buffering. In general, you can use it for input buffering. I've programmed one of these before for a game. It's considered common in like games for the past 30 years, video games, to use some sort of input buffer for reading user inputs. And this is the way I generally input them or implement it, is with a circular array or a ring buffer, because you're expecting it to get a constant stream of things, and you don't need to know the player's input like 100 frames ago, because that's not necessarily relevant to like the way the game controls. So I think that's a good example of where you would use one of these. So what it is, though, is that we keep two things. So we're going to keep 2 pointers. I generally do these as indices, so just integers, but you'll see that the assignment does these as actual pointers, which I think makes it a little bit harder. I have updated the skeleton on Canvas to make it a little bit easier, at least, by introducing a count variable. So I recommend you download that if you haven't already. It's just one extra line. I just added int count that you can use to make things easier. But these 2 things are, let's just say, the write head, which will be in red here, and then the read head. And then if you're expecting things to write and read at a different rate, which is not something that you would expect in a game, I guess, I usually just keep a write head and think that's good enough. And then I would also suggest keeping a count and initializing it to 0 that represents how many things are currently in your buffer. When we do a circular array or a ring buffer, it has these 2 operations, write and read, that correspond to these heads. So whenever you do a write, all it does is it goes to wherever the write head is pointing and it writes a number. So let's say I wanted to write integers into this buffer, and I just write the number 7. Then what it's going to do is put the 7 in there, and then it's going to move the write head to the right of that. Basically, it's just going to write where it's pointing at and then move along. So if I kept going, then it would keep writing. So let's say I write 6, and then I write 4. Then it would insert 4 to where it's pointing, which is index 1, and then update to here. And then it would go ahead and, it would write 6 there. It would write 6 and then move the pointer up to the next spot, and then it would write 4 at that spot and move it up again. I guess we should just keep red. It's basically just writes wherever it's going and then reads as it goes. And I suppose if we do this implementation where it keeps the count, it would also want to increment the count each time, just to let you know how many things are in there. So just so we have an idea. Whoa. I don't know how this got here. Am I able to erase this? Okay. It won't let me control Z it, so I guess we're just going to have a big line going down the middle of the screen. This program's a little weird sometimes. What the write function does, the purpose of it, is to write the thing whether it be a number or a frame of inputs or something like that. And then after that, it's going to go to the next spot. And then increment the count. And there's only really one exception to this, which we'll get to. And now what the read is going to do is anytime we call the read, it doesn't take any arguments because it doesn't need to know what's in our contents of our array here. But the read is just going to read whatever it's pointing at. So in this case, our read head still hasn't moved yet. It's initialized to be pointing at the beginning of the array. And then it's just going to move along to the next spot and return that thing. So this will return 7. And then it doesn't overwrite anything. It doesn't need to actually replace the 7 that's there, because that would take some time to actually overwrite things in our array. And that's part of the reason why you would use this, is that we'll see the write head is going to overwrite things as it goes. All it needs to do is take whatever the count was, decrement it, and then move the read head along. So our read is very similar, just return something instead. So basically store a copy of the thing. Go to the next spot again. Decrement the count, since we are going to have read something from it, and then it will return the copy. So the purpose of this really is just to create an elastic array. Before this read, we had an array that had 7, 6, and 4 in it, and after the array, we've essentially simulated an easy way to do an array where we've gone past the 7 and now it's just 6 and 4. And this is more beneficial than just storing things at the first position and kind of like copying things over, because again, we're just going to overwrite things and we don't need to like copy anything. We just kind of move these pointers along. Right, so our array then, our like applicable relevant array, is just always going to be the numbers between the read head and the write head, where the write is always at the end of the array and the read is always at the beginning of the array, and it's going to kind of just move along as it goes. So let's say we just keep going here. I write 5 and then 2, I guess, and move that along so that the read head, or sorry, the write head is all the way at the end of the array. And then I just do a read so that it ends up here. So let's say that I write the code for that, and it just updates it so that our applicable array is now 4, 5, and 2. The next place we want to write is going to be outside of the bounds of the array. It's going to be over here. So the way we do this, and the reason why we call it a circular array or a ring buffer, is that we want it to wrap around back to the beginning. So the next write we want to do is actually going to be here. Let's say I go ahead and write the number 9. It's going to overwrite that 7 and basically just update the read head. Sorry, the write head. It's going to move it to the beginning again. When you're doing it with the pointers here in the assignment, because it's going to be actual pointers, I suggest you check the end of the array against an address, because that's maybe easier. The reason I do these with integers normally, because I think, again, that's a simpler implementation, is that if we want to wrap around, we talked about it earlier, you could just do a modulo. So if you modulo by the size of this array, actually I should probably just mention that we have a size here as well that was used to allocate this array, I suppose, of 5 things. So the max amount of things this can store before overwriting is 5, regardless of our count, which is currently 4 things now. Right. So one thing to note about that now is as far as the path of the write head, it like wrote here, wrote here, wrote here, wrote here, and then it wrapped around. And the read head still hasn't caught up to it yet. The read head in general is just going to be trying to catch up to the write head at any given point until it actually gets to the end of the array. And just so we're all clear, the array that we have right now is 4, 5, 2, and then 9. So the start of the array is right here, and then we go in this order, and then it wraps around to 9. Now, the important thing to note about this now is that the write head is now to the left of the read head. And that's the first time that this has happened. And that's totally possible if the write head has done a wraparound, but the read head has not done its wraparound yet, that we can get a write head to the left of the read head. And I mentioned that just for the sake of you doing the next assignment, because it is going to require you to check some things, and just be aware that that's not always going to be the case, that the read head is to the left of the write head. If one has done the wraparound and the other hasn't, then just be careful with your conditions. But anyways, we've got this array here. It's now 4, 5, 2, and 9. Let's say we do one more write. And so this writes here, and let's just say it writes the number 0, I guess. What it's going to do, by how we said the write works, is it's going to put the thing there and then move it over and go to the end. And now our count is 5. Now, if you do this implementation with both a read head and a write head, then it's kind of up to you how you want to do a write if it ends up in this scenario. So consider if we were to try to write another number, let's just say the number 3, what would happen by the way our write operation works is it would write into here, write the number 3, and then it would move the write head to here. However, that's kind of an issue because it's overwriting the contents of our array that is still important. The number 4 hasn't been read by the read head yet, therefore it's still probably kind of important. We shouldn't overwrite it. And also because of that, I guess I should put the arrow back, the write head has now lapped the read head. And now, as far as we're concerned, especially if we don't have a count, then the list could be just 1, because now this is in a scenario where these are the things between the read and the write head. It's just the number 3. So what I would argue to do, and what I think the assignment wants you to do as well, is to avoid them overlapping. So in other words, you should check to make sure if the array is completely full, then don't do any writes, because you're going to overwrite your important data and move the pointer to somewhere where it shouldn't be. And that's why I've added this count variable, is to make your life a little bit easier, is you can check if the count is equal to the size, then you know it's completely full. There's a full and an empty variable as well that you can use in that, but I would just suggest checking the size and the count. And the reason why this is a difficult thing to check for, and why I've given you the count variable in the new skeleton, is consider the condition. If we didn't have this count and weren't keeping track of that, the only way we can really know that we've hit this problem is that the read head and the write head are on top of each other, which is valid, but it tells us that the array is full. Now, why might that be a problem if I just check if the write head is equal to the read head? What's my issue if I use that as my condition to check if this thing is full? I guess another question would be, is there any other point at which the write head and the read head might be on top of each other, but the array might not be full? Right, yeah, so I get a response at the start, you're right. And so consider when we started the array, then it was just completely blank, it had nothing in it, but the read head and the write head both started at 0 because we want to start reading and writing at the beginning. So just checking if they are on top of each other is not sufficient, because that's true both when it's empty and when it's full. And actually, just to clarify, it's not just at the start, but also at any points where the array is empty. So at the start it is empty, and then here, if I was to, let's just say read all this stuff, so the read head is right here right now. If I was to read the 4, 5, 2, 9, 0, then the read head would go around here, wrap around, come back, and it would end up back over here, and we would be completely empty. And the contents of the array would also be still full because we haven't been like erasing anything, right? Which we shouldn't. We definitely shouldn't. And in that case, the only thing that we know now is that the count is 0, but the pointers are still on top of each other. The array is still full of things, and so this becomes very difficult to check if you don't keep track of a count, which is why I've added that. So I highly suggest you use that variable, initialize it to 0 in the constructor, increment it as you add things, so you write things to the array, and then decrement it as you read things. And then the only other conditions that you're going to need to check, since we talked about it here, is if the array is full, don't do the write, because you don't want to overwrite anything. And then likewise, if the array was empty, like we have now, where the read head just read all of this stuff and returned it, then you don't want to read if it's empty, because it's going to read either garbage, if we haven't actually gone through the entire array yet, or it's going to read something that still exists from a previous pass through the array. And therefore, you're going to get something meaningless in either case. And again, you're going to kind of misalign the read head and the write head again by letting one race ahead of the other too much. Does that all kind of make sense, like how this works? And again, this is usually useful when you have a constant stream of data and you want to use a limited amount of space, that is. All right, I guess we will move on then. So this is assignment 7. It's just doing this concept, but you're going to do it with pointers. I suggest you use the count variable, and if you ever want to find these two, just consider that you can subtract pointers to find a distance at some point. And again, if you have any questions, just feel free to ask. Okay, so for the last 30 minutes of class, let's talk about the last thing we got to talk about. So the last topic that's in the syllabus is stacks and queues. I just want to talk about the concept behind these, but we'll talk about an implementation a little bit on these. So stacks and queues are ways to do things actually similar to this circular array that we've done, which is actually kind of like a special type of queue, I would argue. And it's a way to store data in order and then be able to get it out in a specific order as well. A queue is something that I think is very common sense. It's something that you expect all the time. So let's say you walk into a store and then you go and get things you want to buy, and the cashier is up here at the desk, and there's some other customers that have walked in. So the order that the cashier is probably going to serve people in is that person A, let's say, walks up to the counter, they get in line, and then person B gets into the counter, and then, gets into the line to go to the counter, and then you get in line. Let's say you're person C. So let's just say this person got here first, this person got here second, and this person got here third, and the order that they're served in, so we'll say this is the order they arrive. The order that these people go up to the cashier and check out is going to be the same order that they arrived in. I don't think it's like in the fact that I have to draw around the UI. Let's move down a little bit. There we go. Right, so that's kind of a common sense way to approach this, right? First person who shows up is the first person to get served. In other words, it's first come, first serve. So the term we use for that is going to be Fifo, which stands for first in, first out. And this is an example of a queue. So queue is just, you start at, an empty queue as people arrive, or objects, whatever it is. You put them into the queue, and then when you want to get somebody out of the queue, when the cashier calls, next please, then you take whoever's at the head of the line. And this could go on. We could add like people D and D here, and they could be arriving at different rates. So the cashier could call person A, and then call person B, and then call person C, and then person E arrives into the line. But we always take whoever's like next in line, right? Is the strategy with a queue. So let's just define with like the special terminology here what those are called. So there's two operations in a queue, and you're going to notice that the stack and the queue basically just share two operations that have different names, but are really just the same thing. So when you enter a queue, it's called an Onq. You just get inside the queue, and then whenever you want to get something out of a queue, it's dequeuing it. If I was to write the equivalent code here, then I would onQ A, I would onQ B, I would onQ C, and then afterwards I would dequeue them all. So onQ is a void operation. It just puts somebody in the queue, and then the dequeue removes somebody. So this returns A first, and then if I did it again, it would return B, and then if I did it again, it would return C. So hopefully that's pretty straightforward. I think these ones are pretty common sense. I'm sure something that everybody does on nearly a daily basis is you just get in a line. Now, the stack is a little less common sense, but is also very useful, and I would argue is more useful than a queue. And rather than being first in, first out, it's going to be LIFO, which is last in, first out. Or you see some people do this the other way around. They'll say like Philo, but I think this is more common, so I'm just going to call it that. And let's just envision it like the name implies as a stack. What we're going to do is we're just going to start with some kind of base, and I'm just going to build up a tower. So let's say instead we have an arrival where A shows up first, and then B shows up second, and then C shows up last. It's a little bit smaller. Oh, that's super laggy. B, and then C, and they show up in that order. So this person shows up first, second, and third. Now the way we're going to do this is we're going to stack these so that the first person goes at the bottom. Or another way to think about this is that they're always going to go at the top of the stack, and it's going to stack them on top of each other. So when we put A into the stack, we're going to put it at the bottom. When we put B into the stack, we're going to put it on top of A. So this is the top right now. And then we throw B on top of that, and now B is at the top. And then we throw C, and then C is at the top. So you can imagine it's almost like a line again, except the thing that shows up last is always at the top. Now, if you envision this like a real stack, where this is just a stack of rocks or something, then you can think, you know, if I remove something that's at the bottom or somewhere in the middle, then the rest of the stack is going to topple over and crash. And the only safe way to remove from a stack then is to remove whatever is at the top. And that's exactly what a stack does. So if I was to now want to remove something from the stack, the order that I would do it in is C first, then B afterwards, because after we remove C, B is on the top, and then A, and then the stack is empty. And so you can see this name comes into play. The last thing that was in was the first thing that came out. So this is our arrival order, and then our removal order is the opposite of that. And again, we can have a scenario where this is kind of kept online, where we add some things, we remove a little bit, we add some more, and then that goes on. Let's just do an example of that really quick. Let's say I have a stack and then we have an arrival where we want to put some things in. So let's first talk about the terminology. So whereas a queue is called on-queuing when you put something into it, when you put something into a stack, it's pushing. Push onto the top. And then whenever you remove something from the stack, it's called a pop. And then we pop from the top. So notice that the focus of this is always the top, whereas the line, we always had a front and a back. This, we just have the top, and that's the only thing that we need to concern ourselves with, because the bottom is never something we want to touch. At least assuming that it's not also the top. Right, so let's say I do this, and I want to do it in the order that I push 4, push 7, push 9, pop. Again, we end up with a similar result here where pushing takes a value being the thing to put into the stack, and then popping is a value returning function that just pops whatever the top of the stack is and then returns it to you. So one does an access and one does a mutation, kind of. And then we push 5, and then we just pop until empty. Pop. And then we would need to pop 2 more times. So let's just say we finish the pop there. So the order of this, it would put a 4 at the bottom of the stack, and this becomes the top. We would put a 7 there, it would put a 9 there, and then it would pop the 9, which means 7 is the new top of it. So it would push these 3 things in, pop the top off of it, push a 5 into it, and then pop the rest of it. So the order of arrival here, just to demonstrate something, our arrival order is 4, 7, 9, 5, and our order of popping or leaving the system, the data structure, is 9, 5, 7, and then 4. Okay. So whereas a queue, the arrival is always going to match the order that it's dequeued in, because that's just how a queue works. It's first come, first serve. A stack is not always backwards. We did an example where it was exactly backwards in terms of the removal order, right? Because we pushed everything and then we popped everything and we didn't kind of like interlace them, right? We just did it in one direction and then immediately went back. So this ended up being the exact opposite, ABC, CBA. But that's not the case if you have some pops in between your pushes. So notice I have a pop here before there's another push. And what happens is that the arrival order is 4, 7, 9, 5, but the reverse order is not 4, 7, 9, 5 backwards. 9 was popped before 5 got in, which means that when we do popping, it's not always the reverse order, but we can almost kind of get that as a clue as to why it would be useful, in that it goes in a reverse order, so it kind of like keeps some sort of history about the things. It just removes whatever the last thing is, and then it kind of goes back to popping to whatever was underneath that. That hopefully gives us some intuition as to why this is useful, is that it keeps some kind of history and then undoes that history. Now, if I phrase it like that, can you tell me of an example that you probably use every day that uses a stack? Not even just programming related, but is there an application that you probably use all the time that does pushing and popping that kind of works in that history way? Control Z. Okay, fair point. So private message, Control Z. You would be right. That is a stack. So I guess there's multiple examples, and we'll see how useful it is then. You're right. Control Z keeps a stack of operations that you've done. Right. Good job. So that one uses history, and then another thing that uses history is something like an internet browser. You have like the back button and the forward button. And whenever you access a page, let's say you go to Google, and then you go to the Google page for, I don't know, computer science, and then you go to the Wikipedia article for that, and then you decide, okay, I'm done reading the Wikipedia article. When you hit the back button, it's going to take that thing off the stack, right? If you clicked on Google first, then computer science search, like query, and then you go to the wiki page, it's going to take you back to the computer science page. And if I then scroll down in the Google search results and click on something like the, I don't know, just Stack Overflow page for computer science or something, Stack Overflow, ironic enough, then that goes at the top of the stack now, right? And I've lost track of where the Wikipedia is because I've overwritten it. I've kind of taken a new path, but this keeps track of history about the pages that you visited. So a stack is useful in that it keeps some sort of historical record that can modify if you take a different path. In this case, we went to the Stack Overflow website instead of Wikipedia, and now that's in my stack instead of Wikipedia, or any pages that I would have had to take in to arrive to Wikipedia that I didn't already back out of. So that's an example of stack. And while we're here, we mentioned Stack Overflow, which is a website, and it's also named after this. Stack is a very common data structure because it keeps this history, and because of that, it's used for one specific thing when you program. So does anybody remember where we could have encountered Stack Overflow if you've had it happen to you before, or a specific topic that we had that caused Stack Overflow pretty commonly? I'll give you a hint. It's something that you use all the time in programming. It is implemented with a stack. It's probably the most common thing, aside from variables, that you use, which would be... So remember, we did recursion, which recursion is when a function calls itself, and that's where Stack Overflow tends to happen, is with functions. So consider if I wrote this code, main, that calls f, and then the function f calls g, and then it calls h, and then g is a function that calls, just say L. Then what happens is main is the starting point. It's like the empty stack, or it's going to have a stack that contains only main. What's going to happen to the stack called the call stack, which keeps track of your functions, is it puts f. It says, okay, I'm going to go execute f. So it jumps here, executes the f code. It says, okay, I'm going to go execute g. Jumps over to g. I guess from here. Jumps over to g. G goes and executes L. We can say L does its stuff, it finishes, it returns. In that case, when a function returns, it pops it off the stack, and it goes and does the next thing. So if G finishes here, then we are done. We're back to F. And then F calls H, so it adds that to the stack, does whatever H does, pops it when it finishes it, pops it when F finishes, and then the stack is empty again, or at least just contains main when you go back to main. So you can kind of see here that when you do a function call, that also keeps some sort of historical record about the order that the functions were called in and where they came from, right? So this, if f is at the bottom, it tells us that f was the thing that started doing all these calls to these things, which is why if you use something like Valgrind, or you just use some general debugger and your program crashes, it's going to give you something called a call stack, which is just going to show you the order that the functions were called in before your program crashed. And that's all this call stack is doing, is it goes and keeps a record of all of these things. It keeps historical data, along with some other things. These stack frames, these blocks here, contain some information about like variables, because you can't necessarily store those all in the processor at once or anything. But yeah, it keeps a stack, which is why if you call a function too many times and this stack grows too tall that it no longer fits in memory, you get stack overflow. And that's what stack overflow is if you just put too many things on the stack and it no longer fits into memory anymore, that is what stack overflow is. So stack is the data structure that is used for function calls, and if you see the other data structure that comes up quite frequently, it's called a heap, and that's for using variables, which we won't cover the heap here. That's something that is talked about in the data structures course. But yeah, that's our usage of a stack, at least common usage of a stack. You can use this for tons of things. It's super useful for implementing algorithms with some sort of historical data about them. Any questions on the difference between a stack and a queue and what they do so far? I don't see... Oh, so question, are stacks or queues more common? I would argue that stacks are. They're really, really important for a lot of things. Even though, again, they don't seem common sense, but I would argue that they're used more commonly in programs. Oh, and another question, could you clarify what Onq and Dq are? Yeah. So Onq is when you insert into the queue. So in our metaphor here with cashier and lining up to check out, onqueuing is when you get into the line, so you get to the end of the line of people, and dequeuing is when you get up to the cashier. So one is the adding procedure and one is the removing procedure, which stack also has it. The adding is a push and the removing is a pop, if that answers your question. Fair enough. I don't think I see any other questions, but if you have any, just stop me. I think we'll briefly talk about how to implement these. I think we'll just talk about stacks first, and then we'll finish queues next time. So I think stacks are actually also easier to implement as well, because we again said that they're focused on the top only. We don't have to focus on having a front and a back of a line like a queue. We can just have the top, and then that's where we add things to, and we also remove things to, which makes this pretty easy, honestly, to implement in two different ways. So the most common way to implement it is with an array, but you are going to stack overflow potentially if you do it that way. If you don't have like privileges like the operating system does, where you just have access to as much memory as you really want, then you might want to do it with a linked list. Let's just talk about the array really quick. The array is pretty easy, and I would generally say it's better. It's what it should do when it actually implements it. So what it does is it just keeps an index to the top of the stack, and whenever you push something into the stack, all it does is it puts that thing there. So it's kind of like our write head that we had earlier. It writes the 4 and then moves to the right, and then writes the 7 and then moves to the right, and now this is where the top is. And so this is pretty easy. It's a super easy operation because all you do is write and then move for the push. And then if we pop, all we have to do is return the thing before it, and then move left in this case. I'm drawing it left to right, but realistically, you could draw this up and down, I guess, as well. So if we pop, then it's going to move the top back here. It won't overwrite the 7, and it'll just leave it there and move to the left. And so these are really just, this is maybe like 3 lines of code because you need to keep a copy when you're returning. But this one, super easy. You just write the thing and then move. So stack, super easy to implement. Code's not particularly hard. It's super useful. The only issue you have is if the top hits the end of the array and goes out of bounds, then you're either going to need to resize it if you have the ability to, or you're just going to have to let the stack overflow, and then, you know, your program crashes. Which, you know, if you make the stack big enough, it's not an issue. Okay, so that's not too bad, I hope. What was the one thing I wanted to mention? Right, I just want to bring up another term. I don't think it'll be on the exam, but it's just something, you know, if you're going around online to be aware of, is that when we do this thing where we just ignore something, right? So when I pushed 2 things and then popped, I left the 7 there, but it's not really part of my stack, and if I was to push again, it would just overwrite it. Like if I pushed an 8, it would just go where the 7 was. When you do this ignoring of something and consider it to be deleted as far as the functionality of your program goes, even though it's still there, that's called a lazy delete, in which you don't actually do any sort of deallocation. You just leave the stuff there and then move. And this is nice because it's faster. You don't have to take the time to actually do the deallocation, go to the operating system and tell it that the memory is no longer needed, which we don't really want to do here anyways. So this general strategy is called a lazy delete. And you'll see it's used for a lot of data structures just in general. Now, this is the way we would do it with an array. Let's go over how we would do it with a linked list. So we can do this with a linked list and not just keep it in a straight line necessarily. But we're going to keep a head pointer, which is just going to be the top of the stack. Again, if we have an empty linked list, that's going to be null. And what we're going to do is, if I was to push something into here, let's say push 4, then all it's going to do is create the node and put it at the head and make it point to null. And then if I was to push another thing, then all it needs to do is it's going to go here, it's going to create the node, and then rather than the normal linked list implementation that we had before, if we're doing a stack, it always just has to insert at the head, right, or the top of the thing. So if we did a push with this, it actually just creates the 7, makes it point to whatever the current head is, and then updates the head to be the new top of the stack. So really all this does is, rather than add at the tail every single time, it adds at the head every single time and just grows leftwards. So the top of the stack in my drawing is just going to go to the left as we add more and more things, and then the bottom of the stack is just going to be here consistently until we get to the end. And again, this code is not particularly hard, right? All we do is we make the new node. We set node equals to new node and construct it. I guess this would be a pointer. Forgive me, I guess this is a pseudocode, but we make a new node. We set the new nodes, I'll just call it ends. We set its next equal to the thing that used to be the top of the stack, the head, and then we just make the head n, and that's it. And the only error checking we have to do is just make sure that the stacks, well, I guess if this is pushing, that's it. We just push and that's it. No need to error check. If the program crashes, then that's not really preventable. So just 3 lines of code, pretty easy. Really quick, let's just finish off with the pop. It will be pretty short, though. I know we're at the end of class, but pop then is just, if we wanted to pop this 7 out, then all we need to do is return this 7 and then update the head so that it moves over to there, so that that's the new top of the stack. Again, this is not particularly complicated in terms of the code. All we would have to do is just keep maybe like a temporary reference to the head, make the head move over to the right by 1 so that it points to the next thing, and then just return the thing that we're popping. So really just 3 lines of code for each of these. They're not particularly in depth with a stack, so it's actually pretty simple to implement. The only exception with the pop here is that if the array, or sorry, the linked list is null, like empty, then you shouldn't pop from it because you're trying to remove things that just don't exist. So that's the only extra thing you need to check. But again, that's like, what, 2 more lines of code? So really not that bad. And again, we can code this if we want to in class, and just come take a look at it. Maybe we'll do that next time. We'll code this and then do the queue stuff. Okay, so that should be everything today. So we'll finish that up next time. We'll probably have some extra time. So again, if there's any topic that you want to talk about, please go to that announcement on Canvas and let me know if there's anything you're interested in. We can definitely talk about it. Doesn't have to be C++ related. If there's any other languages or APIs or anything that you want to talk about, we can definitely talk about it. And assignment 6 is due tonight, so please try to get that in if you can. And I will see you all Thursday then.